Hi, my name is David Dalton. I am an application scientist at Lakeshore Cryotronics, and today I'm going to talk to you about materials characterization at terahertz frequencies. So we'll start today's talk by defining what exactly is terahertz. And so by definition, 1 terahertz is just 10 to the 12 hertz. But for our purposes, terahertz is actually just a slice of the electromagnetic spectrum that lies between the millimeter and infrared regions of the electromagnetic spectrum. And so historically, we've had sources of radiation on either side of this regime, the terahertz gap, so to say. And so for electronic sources have traditionally been used to get to the millimeter ranges, and as well as thermal sources have been used to come down from the infrared sides. In both cases, though, there just simply haven't been enough photons in the terahertz regime. And so this lack of terahertz sources and detectors really left a gap in our understanding of physical phenomena that occurs at these frequencies. So that's changed a lot in the last 20 years, and so there's a bevy of modern terahertz sources, both electronic sources, being backwards wave oscillators and Schottky diodes, and also on the light side, be it infrared sources, quantum cascade lasers, and one of my favorites is the photoconductive Austin switch. So with these modern sources of terahertz radiation, this terahertz gap is now what I would consider no longer a terahertz gap, but actually a terahertz frontier. So we wanted to define what is terahertz. We just have a few words that we can use to understand that. So terahertz really is a relatively unexplored region of the electromagnetic spectrum in which we hope to find new physical phenomena and materials, as well as come across new material characterization methods and develop those material characterization methods. So to understand that a little bit better, what we want to do is we want to go back and we want to unpack some of the conventional optical characterization techniques that have been used in materials for many, many years. And so when we think about conventional optical characterization techniques, what we want to think about is we have an observable, and those observables include things like reflection and transmission, as well as absorption, ellipsometry, as well as the angular scattering of light as light interacts with the material. And from those observables, what we're able to do is, depending on the frequency of light, is derive physical properties of a given material from those observables. And those, depending on the energy or frequency or wavelength of the light, could include things like the crystal structure, the band structure of a material, all the way down into the magnetic excitations that go on in certain materials. So the overall thesis of this part of the talk is really that physical properties of materials are going to couple to different frequencies of light or different energies of light. Right? And so we have a few examples of that. And before we get to those examples, it's really helpful to understand that different scientists use different optical scales or different units for the measurement of light. And so one of those units, of course, is in energy. And so we think about the energy of light. So the energy is just proportional to the frequency of the light. And the proportionality constant is just this h that you see in the equation there, which is just Planck's constant. And so a lot of materials physicists will work in energy scales. When we talk about light, one of the other things that a lot of people talk about is the wavelength of the light. That's just really it's inversely proportional to the frequency of the light, and so higher frequency light has shorter wavelengths, whereas lower frequency light has longer wavelengths. And so we typically measure the wavelength in many different units of length, from millimeters all the way down to nanometers. And finally, the last of our optical scales that we want to talk about is the spectroscopic wave number, and it's just an inverse relation to the wavelength of light, and that's used a lot in spectroscopy by chemists as well as physical spectroscopists, and the typical unit is inverse centimeters. Okay. All right, so some of the examples that we have of different wavelengths of light coupling to different physical phenomena start actually at the very highest energy region of the electromagnetic spectrum. And so we can think about X-ray diffraction, in which the wavelength of light sort of sits between about 0.1 to 1 nanometers. And that's actually the length scale in which atoms in a crystal order themselves in it. So the distance between atoms in a crystal are about a few nanometers apart. And so when we shine X-ray light onto a surface and actually look at the angular scattering of that X-ray radiation, we're actually able to derive the crystal lattice spacing, or the spacing between atoms in that material. Now, of course, we shine longer wavelength light onto a material, that the wavelength is entirely too long to derive that information. So this is one of the physical observables that you can only really get from X-ray diffraction. If we go down in energy from X-ray diffraction down into the ultraviolet regime of the electromagnetic spectrum, the ultraviolet regime has a longer wavelength and is actually less energetic than the X-rays. And so while we're unable to resolve atomic structure in a material, ultraviolet radiation actually has enough energy, in which case you actually can rip off electrons from atoms inside of the crystal. And so by using ultraviolet radiation to eject electrons from a material, we're able to derive some of the energies of those electrons in the material and actually derive band structure of the material. And so this is really important when it comes to understanding the electronic structure of a material and how a material is going to operate. You actually have to understand the band structure. So that's a little bit less energy than X-rays, but still fairly energetic enough to be able to pull electrons out of material. If we go down a little bit further into the electromagnetic spectrum, we're now into the UV visible region of the spectrum. And so this is the visible region of light where we can see objects, and that's what our eyes are accustomed to. It turns out that the UV vis region of the electromagnetic spectrum is actually commensurate with the energy scales that we find in the band gap of many semiconductors. And so what this means is that by shining electromagnetic radiation from the visible part of the spectrum onto a semiconductor, what you're able to do is you're able to promote electrons from the valence band of that semiconductor and promote them into the conduction band of the semiconductor. This promotion process actually corresponds with an absorption of that radiation, that wavelength or that energy of radiation of light. And so certain semiconductor materials which have very small band gaps, for example the indium arsenides and the indium antimonides, are going to absorb radiation all the way from the far red all the way through the UV region, whereas wider band gap semiconductors, for example diamond, actually have very broad band gaps, and so they're actually going to absorb only the highest energy, or the UV region of light. So now we're going to move a little bit farther down in energy to longer wavelengths into the IR region of light. And so in the IR region of light, our wavelengths are now between about 1 and 100 microns, and so these are actually fairly long wavelength, and the energy that corresponds with IR radiation, in fact, is commensurate with what are called phonons. And phonons are really crystal lattice vibrations. And so if you think about in a crystal lattice, you have two different atoms, the red atoms and say the green atoms, and those are actually going to vibrate inside of the crystal. And so when I shine IR wavelength light onto my crystal, when the frequency of the IR radiation matches the frequency of these atom-atom vibrations in your crystal, you're actually able to absorb that wavelength of light. And so in doing this, what you're able to do is you're able to find out something about the crystal vibrations that are going on inside of your material. We're going to go to a little bit lower in energy, skipping over the terahertz regime, and go to our lowest energy region of the electromagnetic spectrum that we're talking about today, and that's in the RF and microwave region. And so this is such low energy and such long wavelengths of light that these can couple to very low energy excitations. And one of the more important of those low energy excitations is actually magnetic resonances. And so the two examples that I give you are that of magnetic resonance imaging, which is used in hospitals all over the world, as well as the electron paramagnetic resonance, which will tell you a little bit about chemical structure of materials. Okay. All right. So we've looked throughout the entire electromagnetic spectrum, and we've realized that different physical properties of the electromagnetic spectrum couple to different energies of light. And one of the more important things that we want to unpack from this is that for most materials, terahertz frequency light really isn't going to directly couple to these typical physical properties. And so we have other conventional probes to couple to those properties, but terahertz simply doesn't couple to these conventional most of these conventional properties. But the really good news is that there's an entire region of the electromagnetic spectrum in which terahertz energy radiation actually can couple to new phenomenon.